So yesterday we looked at a very, very simple model for growth and decay. So today we're going to expand on it a bit. Because we're going to take into account some other maybe external conditions on the problem. Classic example there is if you're measuring temperature, things we know. We know the temperature of an object will never be lower than the temperature of its surroundings. That's if you're cooling something down. You can't cool down below unless you add external things like ice or something like that. And similarly, when you take something out of a fridge, it will heat up, but it won't go past the room temperature unless you apply something to it. So that sort of thing. So we need to change the equation. It's a slight little change. Instead of just being equal to a constant times the, well, P for population, if you like. It's now P minus N. And that N is this external condition. Now the solution to this one, again, we'll see how we solve it next year. But the solution turns out to be, well, there's actually two possible solutions. There is what we call the trivial case, and it is trivial and we're not really interested in it. But it is a possibility that P could equal N. So P could basically be a constant number. If you go back to the differential equation, you'll see that, well, if I sub N in for P, I'll get that P to T is equal to 0. If P is a constant, yes, the derivative would be 0. So that would solve the differential equation. But it's what we call trivial, and we're not really that interested in it. The solution we're interested in is this one. So P equals N plus AE to the KT. Now, if you look at that very closely and think about graphs, what have we got there? We've got that simple model that we saw yesterday, AE to the KT, but we have shifted the curve up or down, depending what N is, that external condition. It basically becomes an asymptote for the graph. It'll rise but never go past it, or come down, never go below it. So N would be the asymptote on our graph. So P, still population we're calling it. The initial population will now be N plus A, because if you sub T equals 0 in, you'll get N plus A. K is still our growth or decay, depending on what's happening, constant. And T is, of course, still time. So we're going to look at the classic one of temperature. T be the temperature inside a room at time. A be the constant outside air temperature. Newton gets the credit for so much stuff, I've got to tell you. Newton's law of cooling states that the rate of change of the temperature is proportional to T minus A. Show that T plus A plus CE to KT, C and K are constants, satisfies the law of cooling. So like yesterday, at this stage, they might just simply ask us to show that it works, show it solves the equation. Well, let's differentiate it. T is A plus CE to the KT. Differentiate that with respect to time. A is a constant, remember, so that goes to 0. And we come up with KCE to the KT. But that's when we rearrange what they've told us. So T equals A plus CE to the KT. I could rearrange that and say, well, CE to the KT is T minus A. Substitute that in, and oh yeah, look, it satisfies the law of cooling. So now we've been given some of those conditions. The outside air temperature is 5 degrees Celsius. A heating system breakdown, or maybe they've drilled a hole in your window, who knows, causes the inside room temperature to drop from 20 to 17 in half an hour. So they want to know, how long is it going to take till that temperature drops to 10 inside the room? We know T will equal 5 plus CE to KT. Remember that? 5 in this case is that external condition, the asymptote, if you like, that won't go above or below depending on where you're starting from. So I know that's 5 plus CE to the KT. Initially, T is 20. Now, if I forgot it's simply A plus C, I could sub in the 0 and work out that, oh yeah, the constant's 15. My equation now is 5 plus 15E to the KT. We can now work out the constants, because they told us that after half an hour, T was 17. So let's sub that in. Make K the subject. Move the 5 over, do a division, log both sides. There's the exact value, 2 log 12 on 15. I'll store that number in my calculator. I don't want to keep writing it down. I'll just keep writing K in my calculations. We want to know when T equals 10. So now I've got to make T the subject of this. All right, again, bit of manipulation. We end up with T is 1 on K, that number I've got stored in my calculator, log of 1/3. Now we just punch some buttons, 2.46167. Remember, I've written log, but we're talking natural log. Make sure you're using the natural log button. So the question was, what was it, after how many hours? Therefore, it's 2.46. So how many hours? That's right, I wrote 2.5. Totally contradicting what I said yesterday. But I just feel it's more natural, 2.46, yeah, 2.5 hours. After 2.5 hours, the temperature has dropped to 10 degrees Celsius. So again, what I was saying yesterday, that's why I do write my actual answer down and then I write my interpretation so they can see, yeah, I did get the right answer. That's just how I've interpreted it. Other than that, it's pretty much the same as yesterday's ones. We've just now got this external condition we have to take into account. 16C.